So today we are going to talk about
waves.
Waves and solitons.
That's right.
Is it sharing?
It's sharing.
It is.
Waves and solitons.
All right. Last time we spoke about waves, and yeah, today we'll continue speaking about waves with more examples. So this is just a recap of the notations and things that we were discussing last time. So gamma, tau, gamma, this is the triple which encodes the graph. A state is a function on gamma. And it's called stable if it's pointwise less than threshold. And then we defined the result of the relaxation, which is a partially defined operator, which projects states, relaxable states to stable states. And then what we finished with was the definition of a wave. It is the relaxation of the forced toppling at a given vertex. So the last formula, WP phi is equal to TV phi circle relaxed. All right. Some definitions. If you have a state phi, then a value at some vertex P is called maximally stable if it's one less than the threshold. And a territory is a maximal by inclusion collection of maximally stable vertices, which is also connected. So this is like a cluster of maximality. Okay.
So in the notes here, you didn't write connected, but it's connected.
Did I write? Connect. Oh yeah, is the maximum subset connected? Yeah, that's crucial. Otherwise, we take just all maximal vertices.
Yeah.
Okay, so this is an important and very easy result that we will prove, which tells you that sending waves from two vertices of the same territory is the same. And so we can speak about sending waves from a territory. Okay? Yeah, the proof is very easy. So take as two adjacent vertices, and if we prove it for adjacent vertices, you continue proceed by induction. Then you prove for any two vertices from the territory, since you can connect them by a chain of adjacent vertices. So how you do this? If you do a toppling at one of the two adjacent vertices, let's say P, then the value at the adjacent vertex Q is exactly the threshold, so you can topple, which means that the result of applying a wave at P to phi is the same as toppling at P, toppling at Q, and then relaxation. So you can start relaxation with toppling at Q. And then you use this trivial fact that topplings commute. Okay, and if you apply the same thing for Q, interchanging P.
I'm a bit lost. I'm a bit lost on the second equality. It says WP of phi is equal by definition to TP of phi.
Yes.
But then, why is this the same as TQ of TP of phi?
What's written above tells you that you can start a relaxation by of TP phi by doing toppling at Q.
But I'm so puzzled. Is this a force toppling at Q?
No, it's what tells you above that the value at Q of the toppling applied at P to phi is equal to the threshold, guarantees that
okay, because they were adjacent. Okay, because they were adjacent. You use that they are adjacent.
Yes.
And then you do that, and then you do that, and then of course, very good, very good.
Okay. So an important remark, nota bene. When you send a wave from some point, it's true that you'll do a toppling once at every point of the territory of this vertex. But there might be more topplings to perform. And below you see the example. Imagine you have all three except for one point where you have two. And so two is naturally excluded from the territory. But if you if you send the wave from the big territory of all these trees, then the value 2 will be 6 after doing topplings everywhere. And so you would need to do a toppling as well where you had 2. So this remark tells you that it's not true that applying a wave from territory is just doing a toppling at every vertex of this territory. There might be more topplings to do.
Mm-hmm.
Okay. But still, this is how you start. So when you apply wave from a territory, first you do toppling at every vertex of the territory, and then you see maybe there are more things to do, maybe there are not.
Mm-hmm.
Yeah. And this is one more example about the subtlety of this, of sending waves. Imagine we fabricated the following state on the whole lattice. So you have all three on the left, all three on the right, and this is separated by the wall of ones, but there is a special place in this wall where one of these ones is shifted by one unit to the right.
Mm-hmm.
Okay. So let's contemplate this picture. You have two territories. If you send away from the territory on the left, it will be just doing topplings at every vertex of this territory, and that's it. So if you do toppling on the left at every vertex, you will not have any more greater than 3 vertices after doing these topplings. You see it?
Yeah, I can see it. I can see it, yeah.
So here it's exactly the case when we did just one toppling at every vertex of the territory, and that's it. But let's see what happens if you do it on the right.
Mm-hmm.
If you do it on the right, one toppling at every vertex, this weird one vertex will acquire 3 grains of sand.
Mm-hmm.
So it will have 4 grains. So we would have to make one more toppling there at this strange site, at this strange vertex. And if you do one toppling there, so let me highlight it. So I'm speaking about this. So this becomes 4. Then it sends 1 grain to the left,
Mm-hmm.
and then you'll do topplings everywhere on the left.
Mm-hmm.
And also you give one more or 2 more grains here and here, which forces it to do topplings. And so actually what will happen is that you will do a toppling everywhere.
Mm-hmm. So, yeah, yes.
So sending away from the right territory is just doing toppling everywhere, so it results in doing nothing. So it's the same state. And this is an important remark to Nikita. In one of the papers, in the paper about solitons, we introduced the concept of a background. And so by that definition, a background is some state on Z square such that there exists a vertex to which we can apply a wave, and it doesn't change the state. So by that definition, it's a background. But I think what I've just explained shows that we shouldn't consider this as a background, and we should revise the definition of the background.
Yeah, you're right. So there, the question was that how to define solitons not only on the state of all three, but also on other like states, like territories. And well, I don't know if it's still interesting or not.
Well, it's just one of the directions. Well, I guess we understand what is a background. Background is something which is like all three, but maybe with sometimes less than three.
Yeah.
So yeah,
but the background is a state where we have the set of all three connected, and maybe something else. And then, according to this definition, your state is not background.
Yeah.
Because the set of all three is not connected.
Okay, that's good. So yeah, that's good. So that's just one of the possible directions to generalize stuff, like to consider not all three, but some other backgrounds. But anyway, but what's important here is that this is subtle. So sometimes doing top links in one territory, doing waves from one territory involves doing top links in some separate territory, but not other way around. So this is not symmetric. Okay.
Nice example.
Yeah. So now we define a soliton. So this I don't like this definition, but still it's what's written in our published paper. So a soliton is a state on the whole lattice. It's a stable state, which is line-shaped. Line-shaped means that where it's different from 3 belongs to some neighborhood of some line. So here BC, so BCL is just some all points P such that there exists Q int L such that P minus Q is less than C. So that's the standard. BCL is just a neighborhood of a line. So
could you? I don't understand the handwriting very well. If it is a line shape, is an R2 line and C bigger than 0, such that where it's not, it's in a neighborhood of the line.
Yes.
And this neighborhood is of length R. What is this?
It's the radius is C. This BCL. And yeah, so you just imagine a strip of some finite thickness, some finite diameter, which goes along a line.
So this diameter could be large or small.
Yeah, it could be large or small, yeah, whatever, but finite. And outside of this strip, you have 3, and inside you might have less than 3. Then also the second thing you ask, it's periodic, and periodic is a standard thing, so it has some integer period. And the last condition is actually the crucial one. It's R movable. Okay. R. So when you apply a wave from outside of this strip, your state is just moved by some vector. So a soliton essentially.
Typically, this R is small or large, or
it depends. First of all, it's not unique, right? Because you can add a periodicity vector to this movability vector. So it can be as large as you want, but it cannot be too small also. But I'll comment on that very soon. Okay, let's consider an example. I think, no, it's not, no, it's not yet an example. So first, the theorem.
But why do you don't like the definition you just made?
Actually, I don't like the last. I mean, it's slightly not concrete. So what is written in the paper is that there exists some point on the plane such that sending away from this point results in moving the state. So I actually think it's much better to just postulate that our solitons, those are periodic and lie. So what I don't like is this point exists from which we send the wave. So I would say very concretely we send waves from big territories, either from one side of the strip or the other.
Mhm.
Okay, but what's important is that for every rational slope, and here I mean the rational slope of this line, there exists a unique soliton up to translation. Okay. So what is important that this periodicity vector can always be chosen to be primitive. And yeah, movability vector is not unique since you can always set to it the periodicity vector. And you have the following equation that p prime q minus q prime p equals plus minus 1. This means that those vectors, movability and periodicity vectors, form a basis of the lattice.
Mhm.
And that's partially answers your question about the size of these vectors. So
Yeah, yeah, it does. It does. There is certain bound there. Yeah, it would be nice to see a picture of what this looks like.
yeah, it's coming. Yeah. So that's a very concrete example of 1-2 soliton. 1-2 means that 1-2 is a periodicity vector. So it's 1-2 periodic state. I don't draw threes as usual.
Mhm.
And it just repeats. So you see 2, 0, 2. Then you shift 2, 0, 2, etc. And let's try to apply a wave from the right. So what happens if you apply the wave from the right?
Mhm.
2 becomes 4.
Mhm.
0 becomes 1. And what's below 2 becomes 1. And what is to the right? So, and what is to the right to the 2 becomes 2. Okay?
Mhm. Mhm.
And so this results on this intermediate picture in the middle, which is not stable. So we just did a toppling at every vertex of this territory to the right. And we got some force,
Mhm.
which we topple. And this results in the thing on the right. So you can do the math, right? So this, for example, becomes 3. This becomes 2. This becomes 3. And this becomes 2. And this becomes 0.
Mhm.
And so what you see that here on the left, what you see as 3 was before the 2. So the moving is like this.
Mhm.
So it's moved by 1, 1. So 1, 1 is the movability vector.
Yeah, but I'm confused. Okay. No, perfect. Perfect. No, it's yeah. Got it.
Okay. Nice. So how do you construct solitons? So to construct a soliton, like what we were doing a lot in the early days of this work, we were generating a big half plane. Just half the lattice, and we would send a lot of waves and see what happens. And what would happen if this wall, this boundary has rational slope? After enough waves, you see the separation of a soliton from the boundary. And then along the boundary, you have some residual deviation, so some trash. Okay, so on the right below, you have two examples, two most basic examples. Like imagine you have a lower half plane, example 1, and you send just one wave. Then immediately you'll see the pattern of all twos. If you send one more wave, this pattern will move down by 1 unit. Make sense? So I'm
say it again. Sorry.
So imagine you have a lower half plane.
Yeah.
And you send a wave from below. Well, it just will make the pattern of all twos along, which goes along the wall. If you send one more wave, these all twos will just move below. And so this is how you construct this horizontal soliton. It's just made of all twos, and nothing is left along the boundary. Same thing, exactly same thing happens for this 45 degrees diagonal half plane. So you'll get the pattern of all ones, and that's the second most simple soliton. And if you send one more wave, all these ones becomes threes, and you get the movement to the right or below. It's the same thing. Okay. And this is the slide I've prepared longest. This is an example, and we will not go through it. I'll just leave it here. So this is an example of generating that soliton that we've seen before, 2-1 soliton, which is made of 202, 202, etc. So I did the calculation. It requires 6 waves to separate this soliton from the boundary. And here you have this residual stuff. You have some stuff left along the boundary, 2-2. The pattern 2-2, 2-2, 2-2. Okay, and here you may see that quite often when you do the wave, there are topplings to perform. After we did one toppling at every vertex of the territory, and then one more, and then one more, so it can take quite long. So that's the third most complicated soliton, and as opposed to the two examples before, the horizontal and the diagonal, 45-degree diagonal, this is already much longer. And I don't remember if we had an asymptotic of how many waves, depending on the slope, you need to detach the soliton, but it can take quite long. All right. Yeah. But it's doable, especially with the computer. It's very easy. So every imaginable slope, you can generate a soliton in a finite time. And all those solitons are beautiful, I find. Okay, so the question now is how big is the APQ soliton? And so this is how you approach the answer. So first, let's denote by phi PQ the PQ periodic soliton. Then consider the projection from the lattice to the quotient of this lattice by the line generated by PQ. And then, since it's periodic, there exists a push forward of the state, which is phi tilde. So this is just pushing forward the state from the lattice to the quotient of the lattice by the line PQ. Okay? So is it clear what is phi tilde?
Then there exists phi tilde to set such phi PQ, the periodic soliton, is the same as phi tilde I'm projecting.
So since it's periodic, you can say it other way around. Anything periodic actually comes as a lift from this quotient by the periodicity vector.
Yeah, you just took the cylinder and.
Yes, that's a cylinder. Well, that's a cylinder. That's right. Discrete cylinder. And so that's the answer to the question how big it is. And so if you consider the total deviation from 3 of this reduced state phi tilde, which is on the cylinder, then it's exactly pi square plus q square.
Very nice, yeah.
So I want to tell you that this is actually the source of the relation to symplectic area. So this is in essence symplectic. Okay, this is the last slide, and let's just look at the examples. I've drawn some solitons. 3 of them we've seen before, and the last one.
Just a second. Again, this is the deviation from 3.
Yes.
The deviation from 3. The actual difference from the sand, the actual weight of the sand or whatever.
Yes, that's the mass, if you like.
And this is the symplectic
area
of the cylinder or of what?
Yes, it's a symplectic. So imagine that those solitons are the edges of tropical curves. Then this p square plus q square will be the coefficient that you need to multiply by the length of the integer valued length, so that you get the symplectic area of the corresponding cylinder. And that's and below this theorem you see how it's computed in practice. So you just take the smallest possible pattern. So for example, for 0, 1 soliton, it's just 2. You take 3 minus 2, and miraculously it's equal to 1 square plus 0 square, or 0 square plus 1 square. And same thing works for all of the patterns. From 3 minus 1 is 2, and 2 is 1 square plus 1 square. 2, 0, 2 is 3 minus 2 plus 3 minus 0 plus 3 minus 2, and this is 5, and 5 is 1 square plus 2 square. So okay, so next time I think we will be able to prove this theorem, and we will consider it as a consequence of a more general machinery, which is largely invented by Nikita Kalinin, which is called smoothings of superharmonic functions.
Very good, very nice, very nice, very nice.
See, now it's not called smoothing. Well, in the next version, it's called, well, I already forgot how it's called. Yeah, because smoothing is like, after smoothing, you have this, something like smooth. But it's not smooth. It's now I call it husking. Like шелушение.
Is it published already?
Not yet, but it's sent to this Arnold journal. Because husking is just like a part by part to remove something.
So okay, I personally like smoothing just because it makes it more smooth. It doesn't make it smooth, but it makes it smoother.
Yeah, you're right. But all the time on every talk when I explain that, then people start to, okay, so how it can be smooth? It's a function with integer values. It cannot be smooth. Like just every time.
Yeah,
I think it's a good idea to create some, this chaos in terminology. Then it helps people to understand something, right? So when you call the same thing in different names. Then maybe one give like work to a student to see what is the difference between husking and smoothing.
So we stop recording.
Very good.